Good morning, everyone, and this is the John Chappell Natural Philosophy Science Chat, where we just get together and talk about what's going on in science, whatever we'd like. So Bob, you mentioned that you had something to talk about having to do with math.
Yeah, math, and what I'm studying mostly these days is classical electrodynamics. If you can show my screen, I can go through it real quick. If not, I can just verbally describe it.
Well, I think you can press the share
screen,
and then you should be able. Now, the trick here is that you actually have to select like the bottom dialog, and then click OK. Otherwise, if you don't select anything, we don't see anything.
Hit that and click share.
So far, I'm not seeing anything. Okay, I see Bob Gray's screen, so I think I have to add that to the screen. Okay, so there we see your screen. There we go.
Okay, I'll assume that you can see my screen.
Yeah, it says Maxwell's Original Equations.
Right, so this guy, Frederick David Tomby, I don't know if that's the correct pronunciation. He's over in Northern Ireland. He writes a lot on Maxwell's electrodynamics. It's pretty good stuff. This caught my eye in particular, Maxwell's Original Equations, and he's looking at Maxwell's 1861 and 1864 papers, and says that there are 20 equations originally from Maxwell from those papers, and he summarizes them here, and then he goes through and describes each of the equations, etc. But what I do when I start looking at classical electrodynamics is ask if there's a way to prove that the collection of equations, 8 equations in this case, are mathematically consistent or not. And so these are Maxwell's Original Equations in modern vector notation from that paper, Tomby's paper. And unfortunately, there's not enough here to go through and prove or disprove that this forms a mathematically consistent system of equations. What I need to do...
well, what exactly would it mean for them to be consistent? Because I could write any two equations,
right?
And they empirically could give the right answers, which I guess Maxwell's equations do. So why would there need to be any relationship between them at all? I know
Lucas
concentrates on combining all these equations, and I've always kind of disagreed with doing that. So what do you mean?
What I mean is that you can mathematically show that the left-hand side of an equation, like equation 2, is equal to, the left-hand side is mathematically equal to the right-hand side. So in fact, it actually is equal. And I'll show a little bit of that further on. But that's what I mean by mathematically consistent. Does the left-hand side of an equation equal the right-hand side of the equation? Can you mathematically show that?
But aren't these just empirical relationships? Or I might have that wrong, but it's just like if you have some quantity, B or H or whatever, and there's something on one side, something on the other side, and theoretically, if you go out in the world and run an experiment, you'll find these things to be true. So is that not the only thing that matters, or is there something else that you think matters?
To me, it matters if it can be done. I think you're right. You go out and do the experiments from the experimental results. You try to postulate a mathematical description. That mathematical description has to be consistent with all the experiments. That's true. And then I say, take those equations, and is there any way that you can mathematically develop a contradiction, a mathematical contradiction, a logical contradiction? And if there is, then there's something wrong with those equations. So let me just go a little further. With those equations, you cannot, from the way that I'm approaching it, develop a prove or disprove that they are mathematically consistent. What I have to do is to add some assumptions, and then we can debate whether or not these assumptions are reasonable or not. But let me just go through them real quick. I'm going to assume that we can use these equations in the case where the charged bodies are in vacuum. So the permeability is the vacuum permeability, and the permittivity is the vacuum permittivity. Now, what was not listed was one of the constitutive equations of Maxwell's electrodynamics. This seems to have been left out of Tomby's paper for some reason. So I'm assuming that we can add that. We make the approximation that the three-dimensional discrete charges positions can be approximated as a mathematical point. I'm not trying to imply that charges are mathematical points, only that it's a okay or good enough approximation that the position of the charged bodies are mathematical points. We will assume that the charge density function can be written for the case of discrete charges as a sum over all the discrete charges with a direct delta function for where they are positioned. As I say, this is math stuff. I'm assuming that the current density function is the charge density function multiplied by a velocity difference. Let me see. There is a velocity in equation 4 up above. That comes in with like the V cross B. And I'm assuming that V is the test charge velocity. And then Tomby says that this is the scalar potential of electrostatics. And from electrostatics, we know how to write that. And then he has a vector potential function, and I'm assuming the vector potential function for the case of discrete charges can be written in this form. Now I can go and check those equations for mathematical consistency. Everything is now written in terms of very fundamental quantities like charge or permittivity or permeability. And because everything has now finally been defined in terms of fundamental quantities, I can go and do the math to see if these 8 equations are mathematically consistent. And so I'm just summarizing some of the equations. This is the equation that I'll check to see if that's mathematically consistent. Does the divergence of E, with E given up here as one of Maxwell's original equations, does that actually equal 1 over the permittivity times the charge density function? And if you put all that stuff in, here's where I'm, questioning whether or not it is actually equal or not. Just do these happy little math steps on and on and on. We find that no, this is not mathematically consistent. So to me, let me see if I can get to a place that can discuss a little bit. It's just, as I say, lots and lots of math.
Well, so you did it for this one equation. Can you explain exactly what that equation is trying to describe? Like, what kind of experiment would you do to show that that was empirically correct? What are we talking about here?
I wouldn't, but an experimentalist, this is just saying that if you have a concentration of charge, the divergence, which is a mathematical term, of the field caused by the charges, in here, I'm trying to highlight 27, equation 27 is
so
what
that's
I'm
what
using.
That upside down triangle is. That's
a divergence.
How does that symbol actually work? Now, I understand what divergence is. Like if you show the field lines coming out of a sphere, you can see that those lines diverge, versus if you had lines of forces coming out of a flat sheet, those would just all go straight up, and those would not diverge. So
Right.
that's what I understand as divergence. But how does that upside down? I think they call that the del operator. I mean, is it really an operator like the multiplication sign?
Yeah, I'm not. Yeah, I'm not going to go into that. I don't have that in front of me to really explain it. But anyway, I do the mathematical development on the left-hand side of that equation, and then on the right-hand side of that equation, and I come up with this mess. And you can clearly see in this equation, clear if my highlighting isn't working. The very last term on this equation 64 includes acceleration, these A's. And as I say, for some reason, I can't highlight the A's.
Okay, well, we can kind of see where your cursor is. So
okay, so these A's stand for the acceleration of the charged bodies, and there is no acceleration on the left-hand side of the equation. So in general, the left-hand side cannot equal the right-hand side. It might under a very special condition, but not in general. And therefore, I say Maxwell's original equations with some reasonable assumptions, and that's debatable, but with those reasonable assumptions, does not form a mathematically consistent system for classical electrodynamics. Then I take a look at experimental inconsistency. There is an experiment called the Maxwell Lodge experiment, where you take a very long solenoid, and there's a slowly oscillating current in that long solenoid, and you put a secondary loop, a secondary wire around the middle of that solenoid, and with a very slowly oscillating current in the big solenoid, it will induce an oscillating current in the secondary. And that's very strange because from the experiment, no magnetic field is experimentally measured outside that long solenoid. So this equation, one of Maxwell's original equations, that B would be 0. And that's what I have here. There is no source current in the secondary, so that's 0. That means the time derivative of the electric field would equal 0. And if that's the case, then there can be no induced EMF in the secondary. But that's contrary to the experimental measurements. Therefore, I say experimentally, Maxwell's electrodynamics is not consistent with experiments. So in this set of notes that I have, I think I've shown that what Tomby is called Maxwell's original equations in vector notation, that's these 8 here, they're not mathematically consistent under these assumptions that I've listed, and they are not experimentally consistent. So I've had some discussions with people on classical electrodynamics in the past, and they said, oh, you can't take the Maxwell electrodynamics out of the modern textbooks because that's not what Maxwell said. That was, something that Havaside took Maxwell's original equations, changed them up, dropped some terms, and so what we have in the textbooks today is not Maxwell's original equations. And I say, well, okay, that's possible, that's fine. Let's go back to Maxwell's original equations, and is that mathematically consistent? And is that mathematically consistent with experiments? And I'm showing here, no, it's not. So going back to Maxwell's original equations doesn't buy you anything. And anyway, that's what I did this past week, and just thought I'd share it.
Although, what exactly is the history of Maxwell's equations? Because it seems that none of these equations are actually attributable to Maxwell. If you look at each one of them, they all have other people's names on them. But yet, Maxwell gets all the credit for these 8. It's like, what? Doesn't that seem true, Bill, that we have Maxwell's equations, but Maxwell had nothing to do with them?
Well, the Maxwell's set of equations that he collected were done by other people, but during the time that Maxwell was collecting them, the empirical equations were being changed because of experiments. And so you can't expect the versions that he had at one particular time to be complete. And so what you have to do is look at the history of each of the empirical equations, which are done by experimentalists, and take the best version that you know of or you can find of each one of those empirical equations. That's what I did when I was doing this work. And
I mean,
also,
is that the history of these equations? These are really just empirically measured things. Now, I find it hard that things like if you're trying to measure the divergence of a charged field, that they're trying to do this like 200 years ago or 100 years or a long time ago, that they would even have the sophistication to be able to do that. I mean, but are these truly empirically derived formulas, or was there just some, like this Heaviside guy, did he go and just theoretically come up with what these things should be? That kind of
Heaviside invented the vector potential. That's not a part of Maxwell's work. And also Maxwell did not work in terms of vectors. He worked in terms of what would you call it? Vectors are three-dimensional, but he had a four-dimensional matrices that he was using, and scientists said, well, we don't know how to work with matrices and stuff like that, so we'll go with Heaviside's version, just using regular vectors, and so that they did that, and so the real equations that Maxwell did are in the form of matrices, kind of like we do for general relativity. When Einstein invented this special and general relativity, he was copying what Maxwell did, and so anyway, that's the issue there. But in my work, what I do is I try to find the best version of every one of the empirical equations, because over time people do more experiments and they may add one or two more terms to the equation. The equations, are experimentally determined. So if you do an experiment that the previous version of the equation can't describe, but it's supposed to, you then figure out what is the kind of term I need to add to it to make it work, and still be consistent with all the other experiments. So that's kind of what they do, and the vector potential has been disproven for some time, and the vector potential says that it is there cannot be a magnetic monopole. That's by definition of the vector potential. There cannot be a magnetic monopole, but you have them probably on your refrigerator if you have refrigerator magnets. You have the kind that are like it has an ad for some business, and then on the back there's a dark brown, what looks like a piece of plastic on it, and you take that and put it up next to the metal door on your refrigerator, and it will stick. If you turn it upside down, not upside down, but to the opposite side, and try to put it against the refrigerator door, it drops to the floor. It won't stick. And if you do experiments with those, you'll discover they are monopole magnets. And so anyway, the vector potential approach, which Oliver Heaviside promoted, has been disproven, and we've had magnetic monopoles for probably 30 or 40 years now, and I have a big collection of them in my house, and I do all kinds of experiments with them, trying to figure out what is going on. How can this magnet work? And
well, how does that even get theoretically proposed? I mean, how does an empirical formula possibly say what can or cannot exist in the physical world? Because an empirical formula is just trying to relate the results of experiments, right? And those
Well, the ones
experiments
that Bob
can't say
showed,
anything about what can exist and what cannot exist.
the equations that Bob showed, when they had the vector potential in there, that's not an experimental equation. The vector potential cannot be measured experimentally. So what you can do if you want to try to introduce that into your theory, you've got to be able to explain various types of data that it predicts. And so the vector potential A predicts that there's no such thing as a magnetic monopole. And there's no way to correct the concept of vector potential to be in agreement with magnetic monopoles. And that's why in my work that I do,
Well, see, that's what I'm trying to get you to explain. Is like I don't understand how that could possibly be. I mean, what about? So what? First of all, what is a vector potential? I mean, I know what vectors are. You know, just like an arrow in space, they have a direction and a magnitude. I know what a vector is, but what is a vector potential, and what does that have to do with monopoles?
Well, the vector potential predicts that del dot B equals 0.
Well,
and del dot B.
That's not explaining to me anything about what you're talking about.
A monopole, then it has only one direction, not two directions, and del dot that type of a vector is going to be 0 if you have regular dipole magnets, north and south poles. But if you don't have both of those, then you have a different property associated with the vector potential and the B field. And so, and the vector potential is defined in terms of the B field. So you have indirectly experimental evidence for that. And in my book that I published, I tried to show what is the best empirical version of each of the what we call Maxwell's equations. But
well, what exactly are Maxwell's equations? So I've got David Toom's paper here. Let me see if I can share that. Since I can share that. Screen share. And for some reason, I can't share. Let me see if I can share that. What are you guys seeing now on the screen? Well, it's just that. That's not what I wanted to share. No, actually, maybe it is, but I got a bunch of ads coming up all over the place here. Let me kill the ads here. Okay, we've got Forky on the top, and okay, well, in any case, so you should be able to see. So that's an example of Maxwell's equations according to David. Now, if I go look at my other favorite source of truth, which is Wikipedia, then I come up with, you know, these 4 equations, which are claimed to be Maxwell's equations. So not only does Maxwell get credit for everybody else's equations like Gauss and Faraday, and but even the number of equations is different. So, you know, Bob, can you explain, you know, why is it we have even this difference here? I mean, is Maxwell's equations like, you know, quantum physics, which could mean possibly anything, or what's going on here?
Not sure what you mean.
Well, David's paper showed like 8 equations. Wikipedia shows 4.
Okay,
right?
So it depends on what you're talking about. If you mean Maxwell's original equations, or if you mean the equations that you find in the textbooks today. Because what is
the difference?
Well, the difference is Heaviside. Heaviside took Maxwell's original equations that were written in component form and in quaternion form and wrote them using Gibbs vector notation and collected them together into a vector system of equations. And when he did that, Heaviside dropped some parts of Maxwell's original equations. And the details of that I can't get into. I don't know precisely. I've read it, and it's, I learn it for a week or two, and then I forget the details again.
But that's not really explaining why is there a difference in the number of equations.
Because Heaviside dropped some terms.
Well, if you drop some terms, that doesn't change the number of equations you have, does it?
I don't know. He maybe not just terms. Maybe he left other things out. Heaviside just edited things down to what Heaviside thought would be the correct set of equations.
Well, are you familiar with, like, on Wikipedia, these four set? Now, I'm familiar with these four. We have Gauss's law, which is the relationship between a static electric field and electric charges that cause it. We have Gauss's law for magnetism that states there are no magnetic charges. And this, I suppose, is directly saying that there are no magnetic monopoles. Gauss's laws for magnetism.
Right.
We have Faraday's law, which is apparently a Faraday's law of induction, describes how time-varying magnetic fields induce an electric field. We have Ampere's law with Maxwell's addition. It says that magnetic fields can be generated in two ways, by electric currents and by changing electric fields. And but I don't see Lorentz force law, which is sometimes thrown into this as well. Now, I can kind of understand what those are now compared to David Toom's paper here. Yeah, okay, here we go. So I'm not exactly sure what these equations A through H are exactly. I mean, these two things don't even look the same.
Notice that there's no potential in the experimental equations, but he's got potentials, A and stuff like that. In his everything that has that potential A in it is from Oliver Heaviside, not from Maxwell.
Yeah, so we have these del cross A things. We've got these rad D things. We've got, like I said, all this stuff. It's just like total Greek to me. So when I look at this stuff, I just get all kind of bleary-eyed, and it's like, no, I can't tell what's going on here. And because of that, I'm just kind of skeptical of things I really don't understand at all. But let's see here. You were showing your paper. You have a specific paper that you had.
Yeah, not so much a paper, just a collection of notes where I go and add to those 8 Maxwell original equations a definition for A, the vector potential, and for C, the scalar potential.
Now, the A there, my understanding was that, A is like something like the cross of B or something. So you have the B field, and then the A field is basically at like, some 90-degree angle or something to that, right? Is that what you think the A field is?
Well, the A field is related to the current density function, and I know in quantum mechanics they use the A field because it's like a momentum. And so in quantum mechanics they have something called a generalized momentum, which is the mass times velocity plus this vector potential aspect, which is also like a field momentum. And that's what they do in quantum mechanics. They use this A. But anyway,
now, in your notes, which one of these equations were you actually picking on? You were like
G.
G. So that's the del dot D equals
Rho.
P rho.
Yeah, it's all Greek.
Yes, it's all Greek to me, and I don't know what these
Okay.
symbols mean at all, right? So,
And I say that because if you look at equation, I think E, okay, which defines what D is. D is equal to epsilon times E.
mm-hmm.
And then you go, the equation just above that is E. And so now you know what E is. And if you put all that back into G, equation G, on the left-hand side, and you put in the definition of what the vector potential is and the scalar potential is, you do the calculation on the left-hand side of G, you do not get rho.
Well, where's rho defined here? Because in order to do
Rho, yeah,
that, you
it's
have to define rho somehow, whatever the
yeah,
heck that
rho
is.
is the charge density function.
So where do you get that from? I don't see rho equaling anything in this A through H here.
That's right.
Rho,
and
as near as
that's
I can tell, is a constant, right?
right. So that is where I add my assumptions that I listed. I listed 8 assumptions, and
So
one
you,
is the definition of what rho is, the definition of what A is, the definition of the scalar potential function.
now somewhere in there, you said that there's an acceleration somehow appearing on
That's
one
right.
of these equations. What is the acceleration? Because most of these things, I think, are measured statically. It's like you have
No,
a charge,
is,
and then
but
you
the
have.
equations A through H are for electrodynamics. So if you look, for example, equation D, there's a partial derivative of A with respect to time. And that A is the vector potential. If the vector potential is related to the current density is a velocity. The charges are moving with a velocity. If you take a time derivative of that, time derivative of velocity is acceleration. So you get an
Time derivative.
acceleration term when you do the calculations.
Well,
It's,
I'm
as I
thinking
say,
that
it's
if you've
math.
got current going through a wire, right?
Yeah.
Now, generally speaking, the voltage available does not depend upon the. Well, maybe it does. I'm just trying to see if there's an actual acceleration here, or whether if you change the voltage, that's not really going to necessarily change the voltage, because voltage is just electron pressure. That's not really saying how fast the electron is going. So the electron could always be going 100 miles an hour, whether it is changing between 0 to 100 volts or 100 back to 0. So that I wouldn't necessarily say that there needs to be an acceleration. I mean, would you agree with that?
Just following the math.
Yeah, but that's kind of like that may be an assumption that maybe you're making, because I'm not sure that acceleration can necessarily be put into this thing here. Now, I can kind of understand time varying stuff, like if you plug a wire into an electrical socket that's varying 60 cycles a second. That's going to give you varying electric and magnetic fields, which I'm guessing the Maxwell's equations are trying to relate. Though I'm not sure that you would necessarily get an acceleration out of that. I guess. So I guess if I were to make a criticism, I would probably say you might want to look there, because once again, my kind of objection is that if this thing has actually been empirically measured, then if you're trying to find a mathematical inconsistency, then I would say, well, you must have made an error, because or I don't know, or either that the equation's wrong, I suppose, would be the other answer, right? Or the equation has certain limitations, right? It's like just like relativity is like Newtonian mechanics holds true, except for when you get to really, really close to the speed of light, in which case it starts doing weird things. And you could say that Newtonian mechanics is just kind of a special case of relativity at low speeds, right?
Yeah.
And maybe that might be part of the problem here, that maybe these kind of things only apply to the situations where the field is changing, but not necessarily having to do with an acceleration. Or the other thing I would think is that sometimes that happens and the acceleration is just zero, and that term just falls out, and it doesn't make any difference. That's kind of like relativity, I suppose. At sufficiently low speeds, none of this stuff makes any difference, right? It's just kind of another, just shooting from the hips here, comment about that. But we're here to discuss, so
yeah. So
anybody else has some comments about what might be going on here, or maybe what the significance is.
I didn't want to take up a lot of time here. Just wanted to let people be aware of what I was doing this past week, the results that I came up with. Willing to discuss these things with anybody offline, so we don't take up a lot of time here, which is just filled with math. So I'd say anybody else have any other topics? Let's get something that's perhaps not so mathematical.
Well, with respect to what you were saying, I just brought up on my screen the list of the empirical equations of electrodynamics, Maxwell's equations, and maybe it would be interesting to see what they are compared to what you were shown in that paper. So if I can I share a screen?
Yeah, you can share a screen.
Okay, let's see.
Yeah, share screen. Typically, click the share your entire screen and then click OK.
Okay, let's see. Can I want to put the here's my screen I want to share. Can you see that screen yet?
No, not yet.
Okay.
So when you get into the share screen dialog, you have to click in the middle of the screen to select your entire screen and then click OK. Okay, so now I see Bill Lucas's screen, but it looks like it's completely blank. Or, no, I think we've seen your screen now. Okay.
Okay. Let's see. I can't see it myself.
So now you need to put something up other than the StreamYard, because right now we're seeing the StreamYard view.
Okay.
So just click on any other tab so that we don't get the, oh, there we go. Okay, so now we're seeing this other paper here.
Okay, this is from my book from the Universal Force. And can you see where my cursor is at the moment?
Yeah, I can see so something about
generalized Ampere's law.
Ampere's law, yeah, Faradays law.
Gauss's electrostatic law. These are the empirical laws of Maxwell. But there are some additional terms in one or two of these that were not known in Maxwell's day, but they were by later experiments as they were revised. But anyway, there's six empirical laws, and there's also the assumption that these other two laws, which I want to show, which are called the Galilean transformation, are valid. That's R prime equals R minus VT, and T prime equals T. And so there's these two they're listed here as 4-7, but it's really two equations. So it's 4-7 and 4-8. There are 8 empirical laws, and notice there's no potential. Oops. Let me get back down here.
Well, quite frankly, I can't notice really anything. It's all, like I said, Greek to me. So when you say there's no potential, I don't know what you're talking about.
Potential energy is not measured experimentally. That is deduced separately. In other words,
potential energy.
Yeah.
So if I take a bowling ball and I lift it like one foot in the air, that has potential energy. That's not anything that's measured in Maxwell's equations.
Yeah, let me see if I can get back to where I was.
But that's potential against, say, electric field or magnetic field.
And this is the name of each of these laws. The generalized Ampere's law, Faraday's law, Gauss's electrostatic law, Gauss's magnetostatic law, Lenz's induction law and Lorenz's force law. Those are the 6 empirical equations of electrodynamics. And
But not
none of
necessarily Maxwell's equations, because once again, I have this big bugaboo about.
these are the ones that Maxwell worked with. And the reason that Heaviside changed the whole approach to electrodynamics to be in terms of the vector and scalar potential is that the experimentalists who were working on the empirical laws assigned the role of the magnetic and the electric field to the Spirit of God. And there was a big second great awakening occurring, spiritual awakening in Europe and America at this time. And that these people were participating in that, and they were complementing it by the way they did electrodynamics. And the people who didn't want any religion and they wanted science to be totally separate from religion, they invented the notion of potentials, vector potential and scalar potential. And they used that instead of the field, because the field, the electric magnetic field, they didn't know what that was. And
well, like I said, I understand vectors because those are the things that they draw on your physics textbook. So they have a north-south magnet, and they show the B field as a vector, which is just an arrow, points in one direction with a certain magnitude. I mean, that part I understand. But does that have to do with what you're talking about, vector potential?
Vector potential is an imaginary thing that was invented by Heaviside in order to get the conversation away from fields, which might be associated with the Spirit of God. They wanted to talk just in terms of potentials. And they wanted
Well, I don't think that that's necessarily bad. I mean, that's why I was asking you, is that vector potential, is that just the vector representation of the magnetic field? I think that's perfectly fine. I mean,
the vector potential cannot explain these equations. The vector potential can only explain these if you modify these equations in a certain way, which is what a Heaviside did, and you ignore Lenz's law and Lorenz's force law.
Well, I still don't understand what you're talking about, vector potential.
You see the first 4 equations.
Yeah, you got first 4 equations, sure.
Okay. Oliver Heaviside's version of Maxwell's equations does not include number 5 and number 6.
Yeah, neither does Wikipedia's version, I guess.
And you see, there's politics going on in science. And for instance, in China,
I mean, I like it better that you call these the electrodynamic equations and stop trying to blame them on Maxwell, because Maxwell's name is not on any of these equations.
No. And
this is just very confusing, right? It's like, what are you talking about, Maxwell's equations? They look like completely different equations every single time I see them in some place, right? It's like, that doesn't make any sense. Can't even agree. Now,
if you look at these equations more closely, you'll discover that including the whoops, my goodness.
That must be Harry laughing. By the way, Harry wants to talk with Bob. So Harry, you are open. So.
Oh, you can hear me. Hey, can I get a
we
word
can hear you.
in edgewise here?
Sure, go ahead, Harry. Yeah, go ahead, Harry. Go for it.
Go ahead.
Am I allowed to speak now?
Yes, speak.
I got some questions for Bob. Let's just start at the beginning, because I'm not really sure what Bob. Okay? I don't understand what Bob's point is, and I don't understand what he's trying to say. And there's been a whole bunch of red herrings introduced. This business of the vector potential. Okay, that's a side issue. Let's not argue about that. Then there's the issue of what Heaviside did. That's a side issue. Let's not talk about that. I want to hear what Bob's point is and what his his thesis
Okay.
is. Comment.
Okay. If
Can we do
oh,
that?
that'd be great. Yeah, that'd be great. So when I look at classical electrodynamics that's in Jackson,
Oh,
yeah. That's in Jackson's textbook or in Griffith's textbook, etc.
I
You get to
still don't
you get
understand. Bob, hold on, Bob. Hold on.
okay, Harry, go ahead.
Yeah, we also have Carl joining us here. So, Carl, to catch you up, you're trying to summarize something that Bob was showing us about Maxwell's equations, and we were discussing, what these Maxwell equations are. I mean, that's my question: is why is it?
Action is not very doesn't work well with this with this software, and I get bits and pieces.
Yeah, you probably want to keep your video off, Harry, to conserve your bandwidth. We can hear you fairly well, though.
There is a delay, but go ahead, Harry. You got a question?
Okay, I'm
Yeah,
getting
Harry.
bits and pieces. That's my point. I'm not getting everything here, and it's kind of garbled. Okay.
Yeah, it sounds like
what
your
I don't
internet
understand is what's.
Go ahead, Harry.
All right, Bob, I don't understand. What is your problem? What is your thesis? Try to say it as simply as you can.
When I take Maxwell's 4 equations as in the textbooks, Jackson or Griffith or others, and I write the E field and B field in terms of the scalar potential and the vector potential functions, and then I write the scalar potential and the vector potential functions in terms of discrete charges, then I can show that Gauss's law, the divergence of E equal to the charge density function, is mathematically inconsistent. The left-hand side does not equal the right-hand side. That's all.
Okay, that means you're doing something wrong with your calculation.
I've been told that what I'm doing wrong is writing the vector potential and the scalar potential in terms of the charges. When you do that, I am told that it is known that Gauss's law does not hold unless you impose other conditions. For example, Coulomb's gauge condition. So in general,
Okay.
Gauss's law does not hold. In general.
Well, that's pretty disturbing. I can see why you're upset by that because it makes no sense to me.
As I say,
I've never heard this. So it sounds to me like somebody's pulling your chain and giving you a line of bull.
But
I've never heard this. Never heard this at all. This is the first time I'm hearing this.
I have.
That's right. You heard it here first.
I have a very.
I think it's BS. I'm sorry. I think it's BS.
Yeah, I do too.
I mean,
I'm trying to. I agree.
As an electrical engineer, I've never heard this. Okay, never heard this in my life. Okay.
Well, Bob is volunteering to send you or anyone else his calculations if you want to review, and that's what we're here to do.
No, but his explanation, that's not what I'm saying. What I'm saying is, if somebody's told him what somebody told you, sounds to me like either you misunderstood it or they were giving you a load of BS.
Well, Bob is inventing
Well,
this stuff, right? This is Bob's
it is
invention.
it is true
Well,
that
he's
when
citing what somebody told him, so I don't know what he said.
it is true that when I do the calculations and I do impose the Coulomb gauge condition, then yes, I can get the left-hand side to equal the right-hand side of Gauss's law. That's true. My point is, when you write Maxwell's equations, for example, at the back cover of any of these textbooks, they do not seem to impose Coulomb's gauge condition. And
What's Coulomb's
when they
gauge condition? What does that mean?
and when they switch to Lorentz gauge condition, they never go back to verify Gauss's law is mathematically correct in the Lorentz gauge condition.
And what are those two things?
Okay,
I mean,
so
just,
your argument has to do with the vagueness of their imposition of the Lorentz versus the Gaussian gauge.
In part, that's right, yes.
Okay, well, now at least we've defined what the issue is.
Yeah, well, I think, we pointed out things about how inductance is, Faraday disk and things like that, which don't seem to work according to the equations anyhow. And now it's either that
All right,
Bob's
let's
wrong,
go back to your
or
I'm not sure what Bob did, so I can't say he's wrong. My question is, in my opinion, okay, what you have is equations, and the one you're talking about is a definition. It just says that charge, if I define what charge is, it's equal to this definition on the other side of the equation.
So, Bob, can you share with us again
Hold
your
on,
notes?
hold on, Bob. Hold on. Bob, do you understand that?
Not completely, because I'm not aware that Maxwell's equations are definitions. I understand current density is a definition, charge density is a definition. The scalar potential function can be defined as something, and the vector potential function can be defined as something. But Maxwell's equations, I have not heard that those are definitions.
Well, why? What else can they be?
Equations of unknown, differential equations of unknown quantities. For example, the electric field and the magnetic field.
All right, let's just take the equation that we're talking about. Which equation are we talking about?
Gauss's law, the divergence of the electric field.
What does Gauss's law say?
The divergence
Show
of
me
the
Gauss's law. Where's Gauss's law?
The divergence of the electric field is equal to the charge density.
That's a definition. Is it?
No, because you don't know what E is. You don't know what the electric field is. Because the way it's written, you don't know what the electric field is.
You can calculate the electric field, right?
If you have the electric field written in terms of charges.
Okay, so I know the charge, okay?
For example, you can write the electric field equal to minus the gradient of a scalar potential minus the time derivative of a vector potential. If you take that definition of the electric field and put it in Gauss's law, you do not get just the charge density function. You also get the divergence of the vector potential function, which need not be zero unless you impose the Coulomb gauge condition. The Coulomb gauge condition is the divergence of the vector potential function equal to 0. That's why that term drops out in Gauss's law. And then you do have the left-hand side equal the right-hand side, but only if you impose that condition, the divergence of A is equal to 0. If you don't impose that condition, there's no guarantee that that term is 0. And so Gauss's law need not hold, as written here, in, for example, the Lorentz gauge condition.
But weren't people like kind of debating whether A actually exists or whether it's just interesting nomenclature?
Okay,
Yeah,
so
people debate whether it's
you're
just math or
essentially
not.
putting in a dynamic condition into well, I understand what Bob did, but I don't think it's correct.
Right. I understand.
I don't think what you're thinking about this correctly, Bob. I think that's what the problem is.
And I'm hoping somebody will be able to, as they say, sort me out
You're
or
mixing up
correct
the
me.
definitions, in my opinion.
I
think that's what
understand.
people have been trying to explain to you.
So then is, for example, well, I don't know, because they're saying I have to impose the Coulomb gauge condition, which means the divergence of A is equal to 0. That's fine, but
I don't understand why you think you want to. You're going backwards in you're used backwards.
I mean, A has something to do with the magnetic field, and no magnetic field should exist around a static charge, right? So why wouldn't A be 0? That's how I kind of see it. It's like, yeah, A is going to be 0 because we're dealing with a static charge. That's what apparently Gauss's law is
the way
saying.
The way that I'm looking at it is I'm looking at Maxwell's equations. One of the first one listed is the divergence of E is equal to charge density. Then I say, okay, this is Maxwell's equations for electrodynamics. Okay, so what is E in electrodynamics? And what I find is it's minus the gradient of the scalar potential minus the time derivative of the vector potential. Put that into Gauss's law.
Now, is this the difference between electrodynamic and electrostatic?
Doesn't equal the right-hand side unless you impose the Coulomb gauge condition. But I don't see Maxwell's equations listed only for the Coulomb gauge. Where in the textbook does it? Here's Maxwell's 4 equations, but hey, only valid in the Coulomb gauge. That's not what they say. They say it's valid in any gauge. Okay, let's use the Lorentz gauge where the divergence of A is not equal to 0. Then Gauss's law doesn't work.
Well, there's Gauss's law. I mean, the Wikipedia here, and I don't know if this means anything, but it's saying the relationship between a static electric field, static meaning not moving, and electric charges that cause it. Now, if you have a static electric field, then the electric charges themselves must be static, which means it's not electrodynamic, it's electrostatic, which is why I'm trying to say, is this a difference between electrostatic or electrodynamics? Because like I said, my point being that if you have a static electric field and static electric charges, the B field around that is going to be 0 because you don't have charges in motion. The A field depends upon the B field being there, so A is obviously going to be 0 in that case. So,
right, but Maxwell's equations, I'm told, is Maxwell's equations of electrodynamics, not
maybe not. Maybe that's where you've gone wrong there. I don't know. I'm probably the person who knows the least about this. I'm only looking at this stuff. But
well, anyway, as I suggest,
that's a possibility there.
We spent an hour on this. I love discussing it, but it's awfully hard to discuss math over this this conference system. So I'd say, anybody else have a different topic?
No, we love this because we're trying to understand. I'm trying to understand, whenever anyone talks about Maxwell equations, I've got all these questions about, well, what really are Maxwell equations? What are Maxwell's equations really trying to say? And when you say that they're mathematically inconsistent, then I want to know, what does that have to do with it? And from the discussion here, Harry has some ideas, perhaps. I have some ideas that maybe this has something to do with the actual static nature of these laws. Because certainly some of them, certainly Gauss's law seems to be particular to the static case. So that would kind of be my explanation, just off the cuff. That why is it that your equations are not valid? But even you yourself say that if A equals 0, then the equations are valid. And to which then I thought, well, A should be 0 because it's talking about static electric field and static charges. So that's kind of the way that I see it. And that didn't involve any math, right? I could explain that without showing any Greek symbols at all, right? But that's generally what I'm good at. I don't like dealing with Greek equations. I would rather deal in the explanatory or the actual physical realization of what's going on here, which is Gauss's law seems fairly straightforward, that if you have an electric charge, that generates an electric field. And Gauss's law describes that for the most part. Wouldn't seem to be that complicated. But yet when we get into the actual equations, we get something that looks like del dot E equals rho over epsilon 0. And it's like, okay, I don't know what any of those things mean, right? So, and I think, people who might be listening might also have the same questions. It's like these Maxwell equations are kind of like something that belong into the priesthood of mathematical physics that, a lot of us just have to our eyes just glaze over when we see this stuff, right? But of course, we're open for comments here, so.
Well, I'd like to make a few comments. That is, with the version of Maxwell's equations that I showed, plus the Galilean transformation, you have 8 equations and 8 unknowns. And they can be solved completely. No vector potential. Vector potential is a false idea. And you are able to now, from electrodynamics, explain all relativistic effects, including gravity. You're able to explain quantum mechanics. You don't need a separate theory of quantum mechanics because the solution to the 8 equations shows that the form of what we call the charge is a toroidal ring. And it comes directly from the solution, mathematical solution of the 8 empirical equations. And,
well, like, how do you get gravity out of a bunch of equations that don't even include gravity, right? That's a little bit of a leap there, isn't it?
The way you get it is you say, okay, I have these things we call charges, and in an atom, the charges can move. And so they can vibrate with respect to one another and form dipoles, quadrupoles, octopoles, etc. So the contribution, and whenever you have a dipole or quadrupole or octopole, and they're vibrating, which they would if there's a temperature, they give off radiation. Okay, and they give off a force due to that vibration. Well, the force is very small compared to the Coulomb force. Just as the force of gravity is 10 to the minus 39th power as strong as the Coulomb force. So,
although, if you have vibratory action going on, generally speaking, that doesn't. The problem with the vibratory forces is that they tend to nullify each other. So any bit forward gets reduced by the amount it goes backwards, and since they're just going backwards and forwards, never causes any net action on the actual object. See, this is the kind of problem with, I mean, only under very, very specific circumstances that I understand can it actually, say, move an object from one place to another using vibratory forces.
Well, let me finish here. In an atom, the electrons are spherically distributed, and the protons are spherically distributed in the nucleus. So what happens is a lot of the forces coming from the vibration do cancel out, but there are, besides the one of our R-squared type forces, there's radial forces rather. There's also R across the field, E or B field type forces, and they're of course very weak. But when you calculate them, you get the strength of the gravitational force. In other words, big G can be calculated from electrodynamics alone. But not only that, these hydrogen and helium, which make up most of the matter in the universe, 77%, they give off what we call the cosmic background radiation, and that is due to the dipole motion. And you can calculate that, and you can calculate the temperature of the universe, and you can calculate the distribution as a function of wavelength of the cosmic background radiation. And you can see when you look at the cosmic background radiation from a galaxy or a star, you can see that it has a higher temperature than it does when it's just in space, just a gas like hydrogen and helium. And so you're able to explain all this phenomena and fit the data just fine, predict what the data that you measured. But you have to solve all 8 of the empirical equations of electrodynamics simultaneously, and you don't modify them with these approximations to throw away certain terms so that you have some logical consistency. And but the reason that all this was done was to get away from the idea that the electric and magnetic fields were emanating from God. And we've done experiments that shows that the excitation of the electric magnetic field produces solitons, which we associate with charge, and all matter, all elementary particles and everything are built from these solitons. And so it's a battle that's being fought between religion and people who don't want to be religious. And so in order to continue this battle, for instance, we changed the scientific method to the existential scientific method, where the role of logic was taken out for the most part. So all the major theories of modern science today are false if you use logic. So they took logic out. And then they had problems.
That's why we're here, because we're trying to prove that, but we're
so
ourselves, I think, illogical as well.
The chemists have known for 50 years that gravity is electromagnetic in nature, and they put it in their journals. Have you ever read it in a physics journal? No. Why is that? Because we now have the postmodern philosophy of science, which says each field of science is a separate silo. It's run by its own people, and what they call truth in one silo is different from truth in another silo. Only if you use logic can you get the truth in all the silos to be the same. But they didn't want that because it isn't supporting the ideas that they wanted. So that's what we have. And so it's crazy. If you want to learn something about something in physics, you've got to go to the chemist, or you got to go to astronomy or some other area where they use a different version of science than you have. And so that's what we see going on. And if you're in one silo and you mention stuff in another silo, you're fired. If you work for a government agency or you work for a university, because the food and I'm not the Department of Energy and the National Science Foundation enforce what we call the education framework, and that is the politically correct version that you're allowed to use in science, in each of the fields of science.
Okay, well, it looks like we've actually have quite a few people on our live stream, at least 14 people, and we have some comments here. So I was going to go through and just kind of show you guys some of the comments here. So we have a comment from David DeHilster. Now, I'm not sure this has anything to do with what we've been discussing here. It's that I'm trying to grasp the idea that models without charge completely dismiss Maxwell's equations based on a model with charge and moving particles. So David wonders whether he's talking about Weber electrodynamics. And Jim wants to know, do we have a reference for chargeless models? And then David says, there are models that don't have charge. Now, me personally, I am not familiar with models that don't have charge. I mean, that would be like denying that, you know, this pencil is in front of my face, right? To deny that charge exists, because experimentally, there's definitely something called a proton, or something definitely has an electron. Those things definitely have charges. So I'm not sure that anyone could really do that. But going on is that electrodynamics is predicated on a moving charge. Models without charge don't have this, and Maxwell gets thrown out as based on a flawed model. Of course, Maxwell's equations have been shown to be empirically true. I mean, no matter what you do, you have to at least recognize that, right?
No.
And I'm not even sure that...
No, because experiments exist now that show Maxwell's equations are not correct. For example, the Maxwell Lodge experiment and the Dabo transformer experiments, it seems to indicate that Maxwell's equations are not correct. And that's experimental results. Of course, with any experiment, there's all kinds of interpretation of the experiment. So, okay, grain of salt as well.
Mm-hmm. So in any case, people are still wondering, what is this model without charge? Like I said, I haven't really held one, but and I'm not even sure what that comment means. And, you know, Stefan once again saying what models don't have charge. And David does reply that Beauchart's ether and infinite universe theory and my father's eyes particle model don't have charge. Although I think even in David's father thing, you know, they base it upon everything upon a different kind of particle. I would just say that I would say that he wouldn't say that things like charges don't exist, but they have a different explanation for what they are, I suppose. So once again, that might be splitting hairs, but that could be a problem. Although right now, currently, we are at 6 people in the live room, and so if you want to speak, then please remain in the live room, and I will call upon you. Otherwise, we need to if David wants to speak, we actually have to make room for him, and someone has to drop off the call if David wants to come and explain what he's talking about. But just going over the other comments here, we have Cornelius, who's on YouTube, and logic would seem to indicate that like mass increase, as the velocity increases, charge likewise increases with the velocity of the charge pattern. I'm not exactly sure that directly addresses what we've been talking about here with Maxwell's equations. But we do have a comment here about the vibratory forces do not balance if the vibration is focused towards a point. And this type of vibration results in particle properties. And vibrations is focused towards a point. And I would say, I know, admittedly, they do have certain experiments where they do try and create the type of focused vibratory forces like that. Although it's still completely unconvincing that you can come up with anything that has the properties of a particle, in particular, the ability to collide in an elastic fashion where things bounce off of each other. Waves just don't ever do that, which is one of my extreme biases against anybody who would say that particles are made out of waves. I think that's just the completely worst idea ever. So but that of course is just my opinion, and I do that because you can never get out of the chicken and the egg thing if you think particles are made out of waves, because waves require a medium which must be made out of a particle that then has to be made of some more waves, which must be mediated in a medium which must be made out of particles, which then must be made out of waves, which must be made out of medium, which must, you see, you can't ever get out of that. So now Cornelius, he does bring up the one situation where you can get a net force out of vibratory action, and that is if you have something here and something there, and they are emitting waves in exactly either in phase or out of phase, then we can get some phase reactions where the waves add or subtract. But that only happens under the very specific circumstances that the waves can actually add, and they have to be at the same frequency, and they have to be a certain distance apart in order for them to either add or subtract. Because normally, if you have two objects and they're ringing at different frequencies, they're going to create beats and stuff like that. But nothing that would create a net force that would take two particles and then cause them to spontaneously separate or come together. Of all the things that happen with charge, that is probably the most mysterious thing that you need to explain, and it's not something I believe you can postulate to just say that a positive attracts a negative and then just leave it at that, right? I don't think you can do that. There is something going on between these two charges, and like so my personal take on that is that they are emitting exactly in phase, same frequency waves, which are either adding or subtracting, and that provides a physical basis for why anything should attract. Oh, look! It looks like we have David here, so I'm going to add David here. So maybe he can explain to us about what he means by a chargeless model.
Hey, Franklin, can you hear me?
We can hear you.
Yeah, actually, there's been chargeless models around for quite a while. People don't look at them. The first one that I saw was Borkert, which he wrote about in the universal cycle theory. It's based on infinity, and a lot of times you're saying, well, it's based on a particle, Well, the infinity idea is, yes, there are no smallest particles. But anyways, to get back to it, Borkert's is an ether theory, which, like my father and I's particle theory, which is also based on an infinite model like that, Borkert's, is that there is no charge. Charge comes from Benjamin Franklin, who wrote a plus and a minus sign on things, and they magically attract. And no one talks about that. Now, if you even talk with people, which I do a lot, who are not like us, who really are into a nerdy level, like all of the people here, which I want to thank everybody for keeping these discussions really great. is that charge is really just a nomenclature we've used to assume that's what, for instance, keeps the electron going around a proton. And it's very convenient for us to put a minus and a plus sign on those things. My dad's an electrical engineer, so there's nobody who knows about charge more than an electrical engineer. And he and I are working on a model that has no charge at all. Now, what I'm saying is, I think it's great to discuss these things, but it must be also known that if these other chargeless models are there, when you're talking about, for instance, moving charges in fields and things like that, it's sort of foreign to me and my father and other people who are working on chargeless models. Like, well, that's interesting, but that's according to a model that I think people subscribe to, but they don't think about what that really means. They don't think about it. It's just like the electric universe people. They talk about the field, and I support everybody's work in the electric universe. All of you guys' work, all of Bill's work. I think that's really important. But we have to be careful about saying, we have this recorded, Franklin, that it's impossible when charge is proved. There's nothing in science that's proved. All we can do is cobble together what we think is the way it works. We can say that these experiments seem to support what we're saying. For instance, in our particle model, we're getting a 7-digit, my dad's getting a 7-digit voltmeter. That's all it is, to test literally parallel resistors in a circuit using our particle model, which has no charge at all. And we've already got some evidence to 70% that the model's predicting a lot different, not a lot different, but different things that electrical engineering predicts. But I think it's just got to be careful. So I just got to be careful, is what I'm saying, is to say that there are no chargeless models out there. That's not true. In fact, we're writing our book right now, and we've been writing our book over the vacation the last 2 weeks. He and I have been working a lot on it. People know about this model. We have my dad has a channel about this model, and like I said, Borkert has in the universe, infinite universe theory model as well. So I'm not here to say or get into discussion. I just think it's important for us to all remember that Maxwell's equations, charge fields are great to talk about, but what happens is, can we understand that we have, I know, for instance, Bill Lucas is talking about, it's a different, different way we're looking at things today. And I greatly admire and support all of Bill's work and everybody's work. But we do have to understand that these chargeless models exist. We're being able to explain things. My father and I are explaining the light, gravity, magnetic fields, electric fields, the double slit experiment. We don't have charged particles moving in a field. So I'm not here to purport that or to say anybody's wrong about it. I just think it's very important for us to constantly remind ourselves that we cannot just only imagine that this is the only type of model. So that was my comment. My comment was just to get it out there. Like I said, there's a lot of people, if you ask the average guy in the street and you say, here, I'm going to draw a picture. The center thing is a proton. I'm going to put a plus on that. And this other thing, this other round circle that goes around it, it's got a minus on that. And those two attract, and that's how they get together. And charge is a fundamental. People are going to go, well, what is that? Why is that? And so I'm not putting this out there as a simple, oh, we don't use it. It is a fundamental question that almost everybody in science asks, but it's never answered. So these models, these two models that I know of are that way, but most models, in fact, do have charge. So that was my comment. I just wanted to get that in there. I just think we have to please be careful before we just say, especially as a moderator, that charge is absolutely known and exists. One of our goals in the CMPS is to support all models, all ideas, because I think that's really important. But again, thank you so much. I want to also just say hello to everybody, and thank you so much for keeping these discussions. I do listen to them and I watch them. I absolutely appreciate, Franklin, your work, Bill, your work, everybody else's who is on here quite regularly. It's greatly stimulating. and everyone has the right to talk about the things they do want to talk about. So I'm here not to say Maxwell's right or wrong, but I just do want you to get, when I see this going on and I'm going, wow, our model is just not this stuff. I just want to make sure that is out there and understandable. But thank you all. 2020, for those who want to know, just really quick for 2 minutes, I don't have the site of our next conference. I'm looking at a lot of things. I'm hoping to have maybe a meeting for all of the people who are interested in the conference to talk about what's going on with conferences, how we do them, and where we could have them, because right now they're being mostly supported by a couple of people donating, and when those people are gone, that's going to be harder to do. So we're going to be, I have a lot of different ideas, but this certainly is helping, and we're getting a lot more people. I know my channel's reaching 3,000 subscribers. So we're out there, and this is a great part of it. So thank you all. I hope that gets some information out there. To answer Jim Marison's question, my father and I are writing a book on this because we've been working on it for 5 years. So it's all based on mechanics, all Principia stuff, Newtonian. So no charge. So anyways, thanks so much, and I will jump off and let everybody else go here.
Okay, but you don't have any current links? Because I think, you
if you go to
have,
the Wikipedia, if you go to the Wikipedia and you look up the particle model, it's on there. It may be somewhat old, but a lot of it's okay and relevant. The book, one of the problems when you come up with this new model, my dad's wave particle duality solution, in the beginning we were just hacking the universe with it, meaning just applying it everywhere and going, feeling like kids in a candy store, being able to do this. Now we're saying, okay, what is it really? And the things we're adding to the Newtonian physics, the things are very clear what we're adding, and we're trying to put that together. So our first attempts at the book weren't really great, but you can go to wiki.naturalphilosophy.org, look it up, and you can get somewhat of an idea about it. It's not super great, but we hope to have in 2020, the book will be coming out. I've written part 1 of it, and part 2 we've got outlined, and we've got tons of stuff that we're writing about it. But you can also read, the only difference between Borchert's work, if you want to read a chargeless model out there, Borchert's work, you can read it in the neo-mechanics section of the universal cycle theory. You can also read about the infinite universe theory, UTF, universe, infinite IUT. And that doesn't have as much detail as we have. We're looking at literally being able to describe mechanically everything that's happening, for instance, in dispersion, why a white light, what it is, how it hits a prism, and how it goes into a rainbow. That's a tough one to hack. But I mean, we're a lot more, tell you exactly what's going on with light gravity, magnetic fields, and all that stuff. So the short answer is it's out on the Wikipedia. Or not Wikipedia.
So what do I search for here? What do I search for here? Because I think I did that. So I'm on the natural philosophy Wikipedia, and
you just search for the particle model. You'll get to us. But again,
the particle model
was a couple years ago. Yeah. Anyways, for those
I'm sharing screen here, so.
Yeah,
and I think we should
get back to what you're doing. In my opinion, because you're talking about. I think this is a different topic for a different day. So I think you should stay here because the people talking here are interested in Maxwell's equations and things. That's my opinion. So for those who
but
want
you're saying Maxwell's equations could be wrong on the fundamental basis that charge doesn't exist, which is admittedly a very radical thing.
Yeah,
right?
but I think
people wanted to know.
But I mean,
people wanted to know. Okay, I mean, it seems like the most interest is like, okay, well, what is that? Because I've never heard of that, right?
Well, yeah, I don't know. Like I said, I think you guys are talking on topics, and I think they should try to stick on a topic. I think if we want to talk about this one day, and you wanted us to talk about chargeless models, I think that would be a topic left. But I think you guys were going on. I was just trying to let people know they exist. And, it's just a different model of the world. I mean, the electron, the particle that goes around the nucleus in our model is done by very different force, and it's done by mechanical force. So, okay.
Let's see. I'm still having difficulty finding any
There's a whole
actual
page on it.
content here on the Wikipedia.
There's a whole page on the particle.
So I found.
There's a whole page on it.
What would I be looking at?
In fact,
it
may be broken a little bit because when we had to upgrade PHP on the server, and I have installed all the exact wiki software, and that exact wiki software is breaking now because we had to upgrade PHP because it's written in PHP. And so I think equations are sort of busticated, and it's one of the 5 billion thousand things I need to do. So it may not be the best resource right now because I think it is busticated a little bit. I did fix some of it, but particle model, I just type that in.
we do have a.
I don't know what you're doing. I just went there and I typed it in, and there's like a huge page. It's just like I said. So I went to wiki.naturalphilosophy.org, went over to the search, typed particle model, and it literally went to the page. I didn't even have to go do anything. So, and it's quite.
Well, you can see I'm sharing the page with you, right? You guys can see the natural philosophy.
I don't see it. I see only
you
me.
Don't see it?
I only see me. No.
Let's see. Am I not sharing? Let's see here. Share screen. Share screen. Share the whole screen. So let's see here. So I'm at the search results. You should see search results, the particle model, search button. Do you guys see that? Or am I not sharing?
Now you are.
Okay, so this is what I get here. So
go to
I put in the particle model.
Go to the home page. Go to the home page.
I go to the main page.
I just did it. I just did it. I literally just did it. Go to the main page. Go up in the very top right-hand sign area.
Yep.
It says view history, and then it says search. Put in particle model, and hit return.
Okay, we put in particle model, and let's see here.
There it is.
So, okay, here we have this page here. Okay.
Okay, but anyways, I think what you should do is just let people know that it's there. But I think you need to get back on the subject because I think this is going to get off of it, and I don't want to do right now.
Well, that's okay because we're just a science chat here, and we're actually just going across different topics, and then we have beaten Maxwell's comments to death. So, but I want to make sure that the people who are watching us on Facebook are getting this. So, let's see if I say post a comment, will that come out?
Anyways, this is really not even close to what we have today, and that's because we've been concentrating on the model. So this is really something we threw together, and it's not really. Did we lose? Did we lose Franklin? Did we lose Franklin? Did we lose Franklin? Did we lose Franklin? I think we lost Franklin. I think he probably had a reboot. Anybody hear me? Say hello. James, do you hear me?
Hello, hi.
Bill, do you hear me?
I can hear you. Hello, Lucas.
Okay, I think what happened when
David, and Bill, and others, I might want to add is that in binary mechanics, there's Franklin back. The two smallest particles or objects are the M and the L one-state bits. I call them energy quanta. And the M-type bit has an electric charge property, but the L-type bit
does not. It has a motion or momentum type property. And that's why the bit function, which replaces the wave function in classical quantum mechanics, the bit function represents both position and momentum at the same time and beats, the tar out of the wave function. So in a way, the chargeless binary mechanics has both. It's got charge in there in the M-type bits as the most elementary object, a one-state energy quanta. And it also has the chargeless L bits. And so you get both, whatever significance that may, or relevance that may have. With regard to errors or problems, either mathematical or experimentally demonstrated in Maxwell's equations, I'm most interested in that, because when we quantize space and time, we eliminate infinitesimal operators, with infinitesimal increments in either position or time. And with respect to time, those would be your time evolution equations for a system state, which is the second central thing after the system state representation itself in quantum theory. And so in binary mechanics, we had to quantize those, and we call those bit operations. And the electrostatic and magnetic are divided into two different bit operations, whereas in conventional force work, they're considered to be one electromagnetic force, as in Maxwell equations and as in the Lorentz force equation. So the only point I'm making here is that I found with computer simulation that the order of these two bit operations for time evolution, or what we call time development of a system state, the order of the electrostatic and magnetic operations, the order that you apply them, matters. In other words, this is a contradiction of the Maxwell equations and the Lorentz force law, where both of those are said or thought to occur simultaneously. Okay, so I just wanted to add those 2 points, that with the M and L type bits, you get both objects, energy quantity that have a charge property, and the L bits, they don't have a charge property. So you sort of get both in the same show, as it were. And the order of the bit operations for time evolution matters, because the electrostatic bit operation is a separate one from the magnetic bit operation, or what I call the vector bit operation. So for that reason, I'm very interested in this work that might show what David Hilscher was talking about in terms of effects that don't depend upon charge, that were previously said to depend upon charge, and or any contradictions in Maxwell equations that others have pointed out. And so I've made the big mistake here of talking a little bit about 2 aspects of my own work, where probably the reason I'm here is to find out about other people's work. So the more we can keep comments directly in our own, it can make this whole discussion more interesting over time. Thank you.
No, well, some of that, since my browser blew up. But so what do you think is the significance of something that you had your bits, some of their bits don't have any charge? And can you name us some phenomenon that don't specifically rely on it?
Every phenomena in binary mechanics, because there are 4 bit operations, and 2 of those bit operations, the momentum one and the strong bit operation, which people don't talk about here much, are required to have correct time evolution. and all the papers showing deriving the speed of light, as I've done previously, or showing the effects on particles in electric and magnetic fields and so forth. It all depends upon those bit operations. So if there's something wrong with those bit operations, those
Well, that
effects
really didn't
would not
answer
show
my
up.
question, because David is bringing up the possibility that charge doesn't exist. You're bringing up the fact that your particles perhaps can be chargeless, although it just seems that mainstream would say that every single particle in the universe, has this property of charge. We've never found ultimately, things that don't have charges. Even things like neutrons seem to be broken down into things which still further have charge.
Well, we have to distinguish between what we call a particle and the M and the L bits, which are constituents of particles. Okay, so there is the two kinds of bits, one with charge, one without charge, carrying an attribute of momentum or directionality, and there's both there. And with that, taking that into account, so far all phenomena that I've attempted to simulate give correct results. So, and what I'm hearing from other people here, and I have to look at these references, and I'm really interested in doing so, is that the Maxwell equations that assume that all of this happens at one time are not exactly correct, and in my opinion, they would be less correct at more microscopic levels.
Well, let's see. Akimbo says to check Wikipedia for something called microscopic formulation. So what is that? Microscopic formulation. Does that come up with anything of any interest here? Not necessarily. Let's see here. Let me share what I'm looking at here. Microscopic formulation. Because once again, we're looking at this idea that there's no such thing as charge, which is a concept which I find extremely foreign, and I am fairly satisfied with mainstream's conclusions that things like electrons exist. Microscopic formulation. No, I don't think that actually brought us up anything.
Well, if you say
relevant.
microscopic formulation, if that's what you're looking for, everything in classical physicists, in classical physics up to modern day, although I'm calling it legacy, quantum theory is a microscopic formulation because it uses real number math, okay? It allows for infinitesimal increments in changes in system state. It allows for infinitesimally different positions in system state representation. So everything that we have that uses real number math is a microscopic formulation. And I rebelled a bit against that and said, well, let's quantize things, space-time and energy, the units of measurement in physics, because everything that we talk about in physics is expressed in terms of those units of measurement, which coincidentally happen to be energy, which you can represent with a mass value, space, which you can represent with a length, and time. And so I went ahead and quantized those. But if you're looking for microscopic formulation, except for binary mechanics, look at anything. Bill Lucas's work is a microscopic formulation by definition. Okay. So it's sort of everywhere. I mean, just Google physics and you'll have microscopic formulations, unless you happen to come up with the binary mechanics papers, which are not microscopic formulations.
George is not microscopic formulations? How could that be?
What is, I didn't hear that, Franklin. What?
You're saying that your binary mechanics is not a microscopic formulation?
Well, if you quantize space into bit loci, which are cubic volumes, in which can only have a 1 or 0 state, and we're going to call, there's two kinds of one state depending upon location of the loci, an M location and an L location. So I call them M quanta and L quanta. And if you look at the length constant, it's about 2/3 of a femtometer. That's fairly darn microscopic, okay? So in that sense, yes, binary mechanics is perhaps the most microscopic thing around.
Yeah, that's what I would think.
Because we're dealing at very small, in terms of length measurements, phenomena. But so yes, you know, like you could say it's probably binary mechanics is the most microscopic gamer in town. But like, unless you want to start positing things that have a size less than the fundamental length constant of binary mechanics.
All right. So did anybody else have any comments on the things that we've been talking about, either Maxwell's equations?
Yeah, now, and in terms of microscopic, Maxwell equations, since they use real-time math, are more microscopic, you might say, than binary mechanics, because you could have any, using real numbers, you could have any distance between two particles. And that's where you get infinities and all kinds of nonsense. And in other words, failure to quantize leads you to logical inconsistencies. And what I'm most interested in some of these papers that have been discussed here, excuse me, is the evidence that this real number version of microscopic gets done, because there's no limit to how small things can be if you're using a real number system.
Well, we got another comment here. He says, Jim, I think maybe you, James, maybe, because there is no Jim, that the microscopic formulation is for chargeless and currentless space. Now, this just may be a difference of opinion here, because if you say that that space is chargeless and currentless, then you would think that's not correct, or you could say that Akimbo is not correct because space is not chargeless at all. You know, for example, people like me who are etherists believe that space is in fact chock full of charges, that the vacuum space is quantized, not only quantized, but quantized because it's like the beach, the sand on the beach, right? It just, there's a bit of grain like everywhere, right? That completely fills space, and it's quantized in that way. So, but the thing is, if you're going to say something about whether the charges exist or charges do not exist, then I think you need to go and look at the experimental evidence, right? Because I think that that's certainly a good thing to go to. So if you're going to say that, you know, if there's no charges, then you have to explain, well, then what is this thing that we've been looking at this whole time that looks like an electron, right? What's this thing that we can shoot from our CRT that hits our screen that lights up the dot that causes CRTs to work? And what is its opposite, the positron, right? What is that, right? If you say there's no charge, I mean, even saying that there is no charge does not sound even a correct way of speaking English, because charge is kind of a field property, right? So it's not like the electron is not the charge, right? The charge is the thing that comes out of the electron. So to say that there is no charge is kind of confusing to me, because it's pretty clear that we have, like, if I comb my hair, and I can use the comb to pick up stuff, and I can use it to attract and repel things. I think those are pretty obvious manifestations of what mainstream calls charge. So in order to try and dismiss that, I find that kind of difficult. So
I think this is Corey. I don't know if I'm on or not.
yeah, we can hear you, Corey. Go ahead.
Okay. I think what David is saying, and I think Jim Marston touched on it too, and I'm just guessing at what David is saying, and I think it's also what Akimbo is saying too, is that charge is not fundamental. Charge is still a derived pattern of energy that it behaves with the characteristic of charge. And it's just same thing. You could say the same thing with mass. Mass is not fundamental. Mass is basically a pattern of energy that exhibits the property of mass. And so I think that might be what David is saying. I haven't read anything about what David's what they're doing there. And I think that's also where Akimbo is headed also, is basically that these are derived properties from patterns of energy, that those particular patterns exhibit the characteristics of charge or exhibit the characteristics of mass. I think that's kind of where that might be going. So to say there's charge or isn't charge, it depends on the state. It's like to say there is ice or there isn't ice in the water. You know, it's either frozen or it's not. It's a state of energy. It's not necessarily that it's fundamental. And I think that might be where it's going. But that's kind of my comment on it.
Well, definitely charge is one of the most mysterious things. If you ask a mainstream scientist, honestly, you know, like I think Lisa Randall answered this honestly, that if they answered the question of what is charge, the honest answer is we don't know. You know, for all of our knowledge, in the mainstream, the honest answer is we don't know. Why is it you take a proton, you put an electron, and for some reason they accelerate towards each other, right?
Right.
Or if you put two protons together, for some reason they just fly away from each other, right?
I want to raise my flag.
No, okay. I've kind of expressed that before to what you just arrived in. We talked about, just you mentioned earlier, about the vibrations in a fluid to a point, and you know, you expressed that there's that attractive characteristic, which is the characteristic which charged particles seem to exhibit, but they don't typically repel as well. And so those fundamental patterns, those vibrations, are not really exhibiting the properties of charge as much as they're exhibiting the properties of mass and gravity. And I've mentioned that kind of before to you. I've also mentioned the fact that you saying the phase matters, that they're in phase, and that's how you explain the negative and positive. But if you actually take those waves and the wavelengths change in length as you get farther away from the focal point, then you'll find that the phase relationship no longer matters. No matter how far away they are, they'll always be attractive, like mass is always attractive. It is more to do with then when you have to actually get some kind of a rotational motion within that pattern as well, that rotational motion can determine a charge characteristic. So you can actually derive charge from a pattern of energy. And I think that's where Akimbo is headed. Maybe where David and his father are headed. The charge is a derived value. And, you know, the attractive characteristic of spheres underwater that you brought up a long time ago is accurate, but the interpretation of it being electrical and being out of phase is probably not, in my view. I've found alternative patterns to explain the characteristic of charge and electromagnetism. Then that particular instance that you demonstrate is more related to gravitational force. And it also goes along with a comment they made a little farther down the line, that Bell Lucas views everything as being gravity as being electromagnetic. But that perfectly spherical wave pattern, or perfectly spherical wave or pattern of energy emanating from those points or going towards those points, is a gravitational pattern and doesn't show any polarization, which is a characteristic of charge in electromagnetics. So that's my comment on it, and I'll just let it go at that.
Well, Jim suggests that charge emerges, like it's an emergent property. It's not anything fundamental, but emerges from the properties of the ether, which is kind of how I see it. That
yeah,
you
it's the same thing. It's the same thing. It's the emergence because it emerges because that particular wave pattern that characterizes, that gives it the characteristic of charge, develops. And so when that pattern develops, then the property of charge, the characteristics and properties of charge interact with each other and exhibit the characteristics of positive and positive repel, negative and negative repel, negative positive. Those patterns emerge out of the vacuum of space or out of the ether, and they develop in the ether, and it's the patterns that basically become the characteristics of charge.
But you still have to kind of explain the physicality behind that. I mean, I think we could probably all agree that charge is some kind of emergent property, but fundamentally from a Newtonian mechanical standpoint, if I have two billiard balls and they're coming together, the only reason why they can do that is if something on the outside rammed into them and caused them to be pushed together. Or similarly, if I see two billiard balls and they're going that way, that's only because somebody hit the two billiard balls with something to cause them to go in opposite directions.
All right. Well, that's going to have to be something for a future discussion because we only got 5 minutes left. But that all can be explained in great detail, and I've gone through it before. But I'm just going to just leave that aside and say the hard part of it, the two solid objects can be emulated, can be shown to be energy patterns.
Okay, so yeah, as you mentioned, we are towards the end here. So we got one last comment here from Adam Lohr, and said, I've described my conception of an ether as being like grains with bits everywhere. So do you mean that the grains are right next to each other or more spread out? Now, I've had quite a few discussions like with Akimbo about this very thing, about whether space is continuous, is it particulate, is it... but this is what I mean. I mean space, the ether, is very similar to the mechanical situation we have with air, like the atmosphere. So what's the mechanical situation we have there? Definitely there are grains, there are oxygen, nitrogen molecules, and definitely they are everywhere. But do I definitely mean that they are right next to each other? And as in a solid, like the beach, right? But I don't think I mean to be as solid as that. I think in order to mediate waves, which I think the ether is the mediator of the waves, you need to have some elasticity in this ether substance. So I would say that it's much closer to a gas or maybe a liquid, maybe not so spaced out as say a gas, but it's definitely not so close that the particles basically cannot move, right? So there must be some elasticity. So that's how I would answer that. So I mean, generally speaking, I believe that the vacuum space is filled with what's essentially neutrons, right? So if you imagine all of space just being chock full of neutrons that are just constantly bashing into each other and just in a very chaotic fashion, that is how I would generally describe what the ether is like. But I believe that brings us to the end of our discussions this week. And if we want to talk about the properties of the ether or how charge works, I mean, definitely the people have ideas on that, then we can do that. And but hopefully we'll see you all next week then.